Okay, welcome everyone. We are very happy to have Dr. Varun Thakre with us. He is at ICTS. He's doing a postdoc here. And today he'll be talking about a hitchin-kobayashi correspondence for generalized seiberg-witten equations. Thank you.
Thank you for the kind introduction. And let me also take this opportunity to thank the organizers for giving me a chance to present my work here. Although this sounds more like a fancy subject that may not seem so much connected with the theme of this conference, I hope to convince you by the end of this talk that there are some interesting cases wherein you can actually see these equations as integrable systems. Fortunately, one of the people I refer here, Sergei Cherkis, I hope I'm pronouncing that right, he's here at the other conference, and towards the end, I would like to point you to his work to see these equations as integrable systems. There's a lot of machinery that goes into defining Dirac operator, the spin Dirac operator. So what I hope to do is to convince you that there is an interesting generalization on R by defining these on R4, and hopefully you'll see that this can be extended to an arbitrary four manifold. Yeah? So let us start with a four-dimensional manifold. Say we just take R4 and look at the trivial spin bundle over R4. So this, by the way, can you read this? Is this? Oh, sorry. So let us start with R4, and you see the trivial spin bundle over R4. This denotes the space of quaternions, by the way. And spinors are nothing but maps from R4 to quaternions. So the first, okay, so in R4, you have your Dirac operator being given by d by dx naught minus I times d by dx1 minus j times d by dx2 by dx3. And we are interested in the maps that satisfy this equation. These are called harmonic maps. So a couple of observations are in order. The first one is that this makes sense on any four manifold, right? So, for instance, you take a four-dimensional manifold, oriented four-dimensional manifold, look at a spin C structure, and these are nothing but the harmonic spinors. There's, of course, a twist given by a connection on your U1 bundle, the determinant bundle, but nonetheless, you can write down this equation. The second observation is that this again makes sense for any hypercomplex manifold. So this is nothing but a manifold of dimension 4n, which is endowed with three orthogonal complex structures in the sense that they satisfy quaternionic relations. So we'll mostly be interested in the case where these are hyperkähler in the sense that you have a metric on M which is compatible with this hypercomplex structure. Okay, so let me define the usual seiberg-witten on R4, and we'll see how the generalization goes through on R4 first. So pick a connection, say A is one form on R4 So I'll just choose the group to be abelian, but you can also do it in the non-abelian setting. So the Lie algebra of U1 is the imaginary real. And then you can define the twisted Dirac operator that has an additional twist due to the connection A. This is the first requirement for the seiberg-witten. And the second one is the following. You look at the self-dual part of your U1 connection, and you require that this be satisfied, where this tau is the quadratic map, where tau of u be 1/2 okay, there's a better way of seeing it. 1/2 u bar times I times u. Oh, sorry. Sorry. Yeah. So tau of u is 1/2 u bar times I times u. So this tau of u is, in fact, what is called as a hyperkähler moment map for a hyperkähler U1 action on the space of quaternions. Right? So what is a hyperkähler moment map? So suppose you have, okay, we can write it in general. So suppose you have an action of a Lie group on your hyperkähler manifold such that it preserves the hyperkähler structure. So it preserves the metric and it preserves the complex structures. Then, under some mild condition, you have the existence of a moment map for each one of these structures. And if you combine them together, you can define a map from M to the Lie algebra C, imaginary quaternions. So this mu is essentially I times u1 plus j times u2 k times u3. This observation is crucial to look at how the generalization works. So, like I mentioned, this also, the Dirac equation also makes sense when your target is replaced by any hyperkähler manifold admitting hyperkähler, say, a U1 action. So for such maps, so let me start. For maps, say for M, I can once again write down such equations. 0 and the self-dual part of the curvature of u goes to 0. Now, if you want to define these equations on, say, non-flat source manifold, there are two ways one can go about it. The first is you either need your source manifold to admit some extra structure, or you need your target manifold to admit some extra symmetries. Right? So what we'll prefer is the second one. We'll ask for additional symmetries on our target manifold. Okay? So if you're convinced that such an operator can be defined on an arbitrary 4 manifold, I won't go into the details of the construction, because as it is, you need quite heavy machinery to do this construction. So suppose X is a 4-dimensional oriented, compact Riemannian manifold. And fix a spin C structure on X. Q. Spin C. This is a spin C principal bundle. Usually you're used to the vector bundle case, choosing a slightly different picture. Right. Like I mentioned, the target needs to have some additional symmetry, so that is what I will discuss now. So first, suppose that M is a hyperkähler manifold. So an action of the group SP1, so SP1 you can identify it with SU2, this is the group of unit quaternions. So an action of SP1 on your hyperkähler manifold is said to be a permuting action if first the action is isometric, and second, if you look at the, so observe that when you have a hyperkähler manifold and you look at the endomorphism, say that is given by Ej plus Ck, such that your A square plus B square plus C square equals to 1, then this is once again a Kähler structure, and in fact, this way you can see that all the Kähler structures on your manifold are parameterized by a two-sphere. So if you look at the induced action of SP1 on this two-sphere of complex structure, then this should be the standard action of SO3 on the two-sphere of complex structures. So that is called as a permuting action. Additionally, what we will require is for this manifold to also admit a tri-Hamiltonian action, that is a hyperkähler action for which a hyperkähler moment map exists. Plus, what we need is, instead of U1, of course, you can take any Lie group. That's fine as well. So we require an action on M that is isometric, and it is tri-Hamiltonian. Right. So and we require that these two actions commute and in fact descend to an action of U2 on M. So this should give you an action of U2. Is this okay till here? Any questions? Okay. So next we will consider this short exact sequence. P1 minus C4 So recall that your group spin C4 is just SP1. So there's a plus copy, there's a minus copy times C1. Modulo plus or minus. That's your spin C4. So the action of the group spin C4, we are going to define it using the short exact sequence, which in a sense means that we require that SP1 minus acts trivially on the hyperkähler manifold. So what you ultimately have is an action of U2 that I just mentioned here. Right. So with this in mind, you have your spin C structure. You have X, and you now look at spin-C4 equivariant maps taking values in M. So by equivariant, I mean that it commutes with the action. So this is another way of saying that we are looking at sections of the associated bundle. Right? But I mean, this figure, rather this approach is more convenient, so I'll stick to the previous one by looking at equivariant maps. So you pick a connection in your principal determinant bundle, that is the U1 bundle, which is given by quotienting your Q with the action of spin 4. And you have the Levi-Civita connection on your base manifold. They together define you a unique connection on your spin C4 bundle. And once again, you can define the generalized Dirac operator and write down the following system. So, I'll write capital A. Okay. Sorry? Yeah, so capital A is the total connection. That's the Levi-Civita plus the small a. Yeah. So that is to emphasize that it's the full connection. Right? And yeah. So this system is called the seiberg-witten equations. And if you change your target manifold and instead of U1 you choose any non-abelian group, then you end up getting various gauge theories that were defined on your 4 manifold, like the pin2 equations, the non-abelian monopole equations. If you replace M with some Hn and choose G to be some non-abelian group that acts on Hn, you end up getting the non-abelian monopole equations. Also, you can get the Waffa-Witten equations and other gauge theoretic equation for various choices of M. Right? So all in all, such a picture allows you to have a uniform treatment of these gauge theories in Go. That's one nice way of looking at it, if you don't have any other motivation to consider this. Right, so one obvious question is that, are there examples of hyperkähler manifolds that have such symmetries, or are we just asking for too much? Well, there are, as it turns out, there are plenty of examples. And the first example is something that also connects with the theme of this conference. That is, these are given by the solutions to Nahm-equations. So solutions to Nahm-equations have this permuting SO3 action, as well as if you choose your group to be large enough, you can of course always get a hyperkähler U1 action as well. So in a sense, this is a large family, by the way. Oh, so the solutions to Nahm-equations, these are hyperkähler manifolds, and they have this rotating, the permuting SP1 action, and the solutions to the, if you look at the solution space to the Nahm-equations, yeah, the solution space to the Nahm-equations. So that gives you a hyperkähler manifold. And if you start off with some big enough group, then you also have the hyperkähler action of G cross G. So there's a left action, there's a right action, and the actions commute with your permuting SO3 actions. So we have a large class of such manifolds. So one essential thing to observe is that we are obtaining this entire family by the hyperkähler quotient of a flat space. Right? And most of the well-known hyperkähler manifolds in literature are obtained this way, either by an infinite hyperkähler reduction or a finite hyperkähler reduction. The second family, and something that I will focus on, are given by what are called as Swann bundles. So to define Swann bundles, I first have to talk about, so I'll take a small digression and talk about the Swann's construction because that will be important for us. So you start out with a quaternionic Kähler manifold. So these are 4n-dimensional manifold whose holonomy is contained inside SPn, SP1, which is defined to be modulo plus or minus 1. So you start off with a quaternionic Kähler manifold of, say, a positive scalar curvature, and you look at the reduction of your SO4n frame bundle to the SPn SP1 bundle. So call it some P. If I quotient my P with the action of SPn, then what I end up getting is a principal. This is the SO3 bundle. So this is nothing but the frame bundle that is associated to the local quaternionic structure on N. Right? Now, look at a metric cone over this Sn. So I call it, say, Un. This is Sn cross plus with the metric being given by so R is the radial coordinate of Sn. So this is a fantastic result by Swann that says that Un is in fact a Kähler manifold, and it also admits the permuting SP1 action. And say, suppose you have an action of a Lie group on N that preserves the quaternionic Kähler structure, then you can always lift the action to Un such that the action is tri-Hamiltonian on Un and commutes with the permuting action. So what are some simple examples? Look at the quaternionic projective space, right? And this Sn is nothing but, right, so this is, right, Spn plus 1 modulo Spn. Yeah? And when you take the metric cone over this is nothing but your Hn minus the 0. These are some simple, straightforward examples of Swann bundles. You have more interesting examples like the instantons, the SUR instantons on R4 of charge n. These can be obtained as Swann bundles over some quaternionic Kähler manifold. Then you have the complex Grassmannians, which have the quaternionic Kähler structure, and you look at the cones over them, you again obtain a nice hyperkähler manifold. So one interesting property that I will use ahead is the following. You see, on this cone, you have a natural action of R plus, right? And suppose there is a group action such that a hyperkähler moment map exists. You look at some positive function times U acting on U, then this is nothing but e to the 2f times mu. So in some sense, your moment map is quadratic in nature. And this is a property that is most crucially used in the second part of this talk. Let me erase this part. So suppose that we are looking at the generalized seiberg-witten equations, and our target hyperkähler manifold is the total space of some Swann bundle. Okay? For such manifolds, there is a nice characterization, not so much characterization, but an interesting result to begin with. Right. So this theorem was proved by myself. Oh, so before I state this result, I would like to state Donaldson's result. This is by Donaldson in 2002, I guess. 2001. So the third reference. So the result is as follows. The solutions to the usual seiberg-witten equations are in one-to-one correspondence with self-dual two forms on X that satisfy the following PD away from its zero set. So have plus star Abanov omega equals to minus. So Sx is the scalar curvature of X. Self-dual two forms omega. Minus twice. There's this pairing, the details of which I won't get into. Of time. One half mod of the omega square by mod of omega square minus n omega square. N omega is the Nijgen-Huey tensor of omega plus mod of E of mod of omega square, hot star of P of omega, P of mod of omega, The question is, can we say something similar about the solutions to the generalized seiberg-witten equations? And the answer is, indeed, we can say something similar when the target is the total space of the Swann bundle. So this theorem is as follows. So suppose A comma Q is a solution to the generalized then away from its zeros, mu of u, remember mu of u can be identified with the self-dual 2 form. So away from its zero, mu of u satisfies this PD, I'll call this 1, satisfies 1. I'm slightly cheating here when I say it can be any Swann bundle. In proving this, one actually uses the fact that the hyperkähler manifold can be obtained as a reduction of a flat space. But this is true in most cases, so there is not much loss of generality here. And what this says is that if mu of u satisfies this condition, then we, in fact, if we restrict our spinor bundle to x minus the zeros of mu of u, then you can always find a non-vanishing spinor such that you can write mu of u as some tau of phi, where phi is your spinor and tau is the quadratic map. Yeah. Yeah, there's also omega over mod of omega square, I think. The second term is a 2 form. That's what I said. I don't get into this pairing, but this is something like this. This is a 1,2 tensor, and you can identify this term with 1. So what you get is a 0,2. Any questions? This has some interesting consequences that I will get to now. This is precisely, so using this fact and the quadratic nature of our moment map, these are the 2 crucial ingredients to proving the hitchin-kobayashi correspondence. Can I use this part? Right. So, right. So first of all, recall that I mentioned that we require that the action of sp1 minus on a hyperkähler manifold should be trivial. So we are, in a sense, looking at this bundle, right? I know if I have not used the letter before, let's call it. I have used it. Okay, let's call it p hat. Okay. So your spinors were, in a sense, mapped from p hat to m, right? And p hat is a u2 plus bundle, right? So suppose your base manifold is scalar. What does that mean? It means that there is a reduction of the principal SO3 bundle, SO3 plus bundle, that is the frame bundle of the self-dual 2 forms, to a principal U1 bundle. And that, in a sense, gives you a reduction of p hat to a principal T2 bundle, where this T2 is U1. I'll denote this by R because this is a permuting action. I'll mention in a moment what this action is. U1, this U1 is for, without any suffix, is for the hyperkähler action, so minus 1. And let me state this lemma. So suppose G prime is a subgroup of a group, and say you denote by P prime the principal G prime bundle over your manifold. And define P by PG hat to be the principal G bundle. Right? Then if you look at equivariant G equivariant maps from PG to M, it's the same as looking at equivariant maps from PG prime to M that are equivariant with G prime. What is the consequence of this? Is that the consequence is that if the base manifold is scalar, then looking at equivariant maps from your principal spin C bundle into M is the same as looking at equivariant maps from your principal T2 bundle into M. Right? So a corollary is that you have the isomorphism E plus M is plus P T2 M, that is T2 equivariant. This yeah, G prime over G prime over G prime. Yeah. Yeah, just a subgroup. Yeah. Okay. So on a Kähler manifolds, our equations reduce to the following system. So this is a theorem by Haydys. This thesis, so I believe 2006. That's there in his thesis. So the generalized seiberg-witten equations reduce to the following system. This is given by del power AQ goes to 0. This is your usual Cauchy-Riemann operator twisted with a connection. You have the self-dual part of the curvature, or well, plus mu1 of u. Omega x is the Kähler-2 form on your base manifold. Have the 0,2 part and the 2,0 part of A vanishing. And mu c of u goes to 0, where your mu c is the complex moment map that is given simply by mu2 plus I times mu3. So this is quite similar to the symplectic vortex equations, where your target is some symplectic or a Kähler manifold. The basic difference is that we have an additional twisting due to the Levi-Civita connection that we don't usually see in the symplectic vortices. So this capital A is to precisely emphasize that fact. Any questions? Okay. Okay. So what exactly is the Hitchin-Kobayashi correspondence in age-theoretic sense? Roughly speaking, or not too roughly speaking, but it's the GIT in infinite dimensions, right? If you observe, let's say your C is your configuration space, that is the space of maps from PT2 to M to equivariant, and the space of connections on your principal determinant bundle. Let me write determinant bundle. Then you have on this configuration space an action of your gauge group, which is nothing but maps from X to Q1. There's a canonical Kähler structure on the configuration space, and therefore this action extends to an action of the complexified gauge group. Right? So if you look at the equations, the first and the third equation are invariant under the action of the complexified gauge group, but that is not the case with the second equation. This is not invariant under the action of complexified gauge group, only the action of gauge group. So the question is, does there exist an element in GC such that this equation is satisfied? Okay. So for that, I'll be considering the perturbed equation with a perturbation tau. And this is the essence of hitchin-kobayashi correspondence. So I would like to remark here that in the case of symplectic vortices, there is a much general version of such a hitchin-kobayashi correspondence, which has been proved by Riera. This is the most general case, but explicitly evaluating this, the stability condition there is quite a difficult task. So the novelty in our proof lies on the fact that the hitchin-kobayashi correspondence narrows down to studying the existence and uniqueness of solutions to Kasdan-Warner equations. Okay, so let me state that. Which part can I erase? Okay. Right. I mean, the question is existence and uniqueness. So first, does there exist an element of the complexified gauge group such that this equation is invariant under that? Right? The first and the third are already invariant under that action, so it won't affect them, but it will affect this equation. Right? And the second question is it unique? Right? So here's the theorem. Uh, 2018. Right. So the statement of the theorem is as follows. So let me introduce a couple of notations before I state the theorem. So we have, say, H11 is the space of all elements in the configuration space such that your first equation and the second equation is satisfied. I don't really need for this equation to be satisfied for this correspondence. I just need the second and the third equation. The first sort of cuts out a complex submanifold in the space of solutions to the last two equations. And suppose your F0 in M is the set of fixed points of the hyperkähler U1 action. Define S to be set of U comma A in H11 such that the image is not entirely contained in this. So what this says is that mu of u should not be identically 0. You understand? Okay. So the statement is as follows. Let your tau be greater than 4 pi on volume of x, degree of your determined bundle. So this is just the integral of your curvature on your manifold. Then the moduli space admits a holomorphic description. That is, you can write your moduli space as SS modulo the action of the complexified gauge group. This is precisely GIT, the Kähler case, right? So I'll just give a sketch of the proof, a little sketch of the proof to see where exactly is the fact that it narrows down to Kasdan-Warner used. So how does, so let's take an element in complexified gauge group. If my F is purely imaginary, then this is just an element of the gauge group, and we know that the equations are gauge invariant. So there's no point in considering that case. So what we'll do is we'll instead consider F to be purely real. Okay? There's no imaginary component. So e to the F is a non-vanishing function. How does this act on the connection? So this action maps it to A plus del F bar minus del bar F. Okay? So if you compute, this is the contraction with the Kähler 2 form on the base manifold. If you compute this is A minus Laplacian of F. On the other hand, recall what I had said about the moment map. That is true for each one of the moment maps. So therefore, this is nothing but e to the 2f times mu1 of u. Right? So what does the curvature equation become? The equation, I'll skip the computational details, the equation simply becomes this plus e to the 2f times a of u, where I'll mention what is a of u, equals to tau minus I times fe. Should be small. Right? Where my a of u is nothing but minus m, the fundamental vector field due to the basis element psi1 of sp1 along u, and this is the fundamental vector field due to the u1 action along u. So this defines a real valued function on your base manifold. And recall the previous result that says that away from its zeros, you can always write down this a of u as some mod of phi square, which means that it is also positive away from its zeros. Right? So what does Kasdan-Warner say? Kasdan-Warner says that if your a of u is positive away from certain measure zero set, and the integral of this quantity is positive, then there exists a unique f satisfying your equation. Oh, sorry. So, yes, you're right. So I need a better notation. Okay, I'm using B for the lack of good notation at the moment. So. Yeah. Thanks. Right, so what does it mean for this quantity to be positive? This is precisely this condition. Right? This is the degree of your principal U1 bundle. So it narrows down to looking at the existence and uniqueness of Kastan-Warner equations. This is a much simpler proof of hitchin-kobayashi, at least in the abelian case. And it is also possible to extend this to the case of symplectic vortices, where you're looking at Kähler cones. Similar argument works there as well. So so all in all, you have such a holomorphic description. That's about the hitchin-kobayashi part. I think there are just 4 minutes left still. So I promised you that towards the end of the talk, I'll mention at least one interesting case where this thing, these equations become an integrable system. So for this, I refer you to the 4th reference of Cherkis. If you look at the total space of a spin bundle over a 4 manifold, then that has what is called as a spin 7 structure. Okay? And there is this, there are what are called as the higher dimensional instantons, like the spin 7 instantons. They satisfy similar equations to the instantons in 4 dimensions. You look at spin 7 instantons. Let me just tell you the picture on R4 so it's easier. On R4, this is the total space of your spin bundle. Let me just call this W plus. So look at spin 7 instantons on your total space and look at the solutions that are invariant in the direction of W plus. So that is, you're performing a certain dimensional reduction of spin 7 instantons. Then it narrows down to a system of generalized seiberg-witten equations where your target is nothing but the space of 1 forms on R4 with values in the Lie algebra. The spin 7 Lie algebra, I guess, yeah. I have to check that, but yeah. This is the, how do you say, equivalent of Hitchin's self-duality equations in 4 dimensions. Right? So the equations look something like this. You have the A of phi, where phi is your Higgs field, and you have phi. Right? And of course, the instanton equations and all of its possible reductions are again integrable systems. So this is one nice instance where you have this. You can play the same game in 3 dimensions as well. You look at the total space of the spin bundle and you have a G2 structure. You can play the same game. And you should in all probability get an integrable system as well. So of course, as you keep changing your target, you might come across instances where this becomes an integrable systems. So this is the closest possible connection to the integrable systems that these equations have. Maybe the Kähler case gives something more, I don't know. But yeah, that's it from me for the moment. Thank you. Thank you. It's a pleasure. Geometry, not much at the moment. I'm still studying this, but there is a hope of compactification. There's a recent result by Alexander Doan, I guess. Yeah, Alexander Doan, where he has studied these Seiberg-Witten with multiple spinners, And you can look at this case, this moduli space as sitting inside the moduli space of solutions to seiberg-witten with multiple spinors. And that he has shown in the Kähler case is actually compact. So there is a hope of compactifying this, and from there, at the moment, I don't know what to expect of this. No, there is, I mean, there's an obviously a Kähler structure on this that is present. But I think his question was, do you expect something more from this? Or at the moment, no. I mean, Kähler structure is the standard one, the natural one that is induced from the configuration space itself. From the configuration space itself. It would be interesting to see, for instance, if this admits some extra structure like a Kähler potential or something else. At the moment, I don't know. Yeah. Thank you so much. Thank you for the opportunity.